So why is this previous mentioned hypothesis so relevant? And in the back here you see this empty lecture hall, but at 9 o'clock it will be filled with students. And then what we do? We sit for 2 hours long. So not much energy is used compared to when we do physical activities. Okay, we talk a little bit, we stand up, we cross our legs, we use our brain. There is some brain activity, I hope. So our food intake is quite important if our energy expenditure is that low, and we do not want to join a club of obesity. And because carbohydrates are our main source of energy intake by far, we decided to study the effects of glucose and sucrose on energy expenditure. We're going to measuring the oxygen and CO2 expenditure. First, we're going to do 30 minutes in the resting state by both the participants. Afterwards, after those 30 minutes, we're going to give one of the participants glucose, the other one sucrose. And after those 30 minutes, we're going to alter it. The study we conducted, our experiment, is a double-blind study, being that both participants and the researchers didn't know which drinks were given, first glucose or sucrose, or vice versa. Our pool of subjects is non-randomly selected, being students at University of Maastricht faculty FHML, Site Biology. Above you can see Julia, that's our first participant. Afterwards you can see Stasha, that's our second participant. Stasha had breakfast before, but due to a lack of participants we had to include her in the results. Both of the participants signed an informed consent, so they know the participation was not anonymous, and also the results can be made public. The method used in this experiment is calorimetry, and this is a science of measuring the amount of heat generated exothermic or consumed endothermic. Energy expenditure can be determined by measuring the heat production from consuming substrates such as carbohydrates, fats, or protein. But in this case, we're going to use carbohydrates, being the monosaccharide glucose and being the disaccharide sucrose. Furthermore, we're going to measure the respiratory coefficient, and this is the relationship between the volume of oxygen and the volume of carbon dioxide, and this is determined by the substrate being consumed, mentioned earlier. In this chart, you can see the oxygen levels and the carbon dioxide levels, and this is going to determine the resting coefficient, the RQ. The RQ is needed for determining or interpreting the resting energy expenditure. This is measured in a kilojoule. This also can be measured in kilocalories. 1 kilocalorie is, or 1 calorie is 4.2 joule. But this is just how you want to do it. Furthermore, you can see the protein oxidation, fat oxidation, and the carbohydrate oxidation.
In this first graph, you can see that participant 2 has higher values for CO2 and O2. Participant 1 has a higher value for O2, while participant 2 has a higher value for CO2. The mean RQ in resting state was calculated for both the participants. Participant 2 has a higher value than participant 1. The REE is also calculated using a formula and the CO2 and O2 values of the participants. The REE is calculated in fasting state, after taking sucrose, and after taking glucose. At least the REE difference was calculated between fasting state and after taking the drink. As you can see in the graph, the REE after taking glucose and the REE difference are higher than the REE after taking sucrose. Before ingestion, the mean REE was higher for participant 2 than 1. After the first drinks, the REE increased for both the participants. After the second drink, only the REE of participant 2 decreased. At least the fat and carbohydrate oxidation was measured. For participant 1, the carbohydrate oxidation increased a lot after taking the first drink, sucrose. At the same time, the fat oxidation decreased a lot. After the second drink, glucose, the values didn't change a lot, only the fat oxidation slightly increased. For participant 2, the carbohydrate oxidation didn't really increase after taking glucose, but it really did increase after taking the sucrose. The fat oxidation slightly increased after taking the glucose, but decreased a lot after taking sucrose.
The answer on the research question, whether the intake of sucrose or glucose gives the highest energy expenditure in rest, is that glucose gives the highest energy expenditure. But this is against the hypothesis that sucrose will give the highest energy expenditure because of its molecular structure. Sucrose contains glucose and fructose, so it would give more energy because there can be more ATP produced because the citric acid cycle occurs more than with glucose. A possible reason for the contradictory results with the hypothesis is because of the breakfast that one participant had before the measurements. Because of the breakfast, that participant's metabolism was already awake, so it could be that that's the reason why the glucose gives more energy than the sucrose. In general, the breakfast of one participant should be seen as a bias in the research, but because of logistic problems with the actual participant, this was inevitable. The group of participants is also very small to consider the results as generalizable, but they do give an idea of how the oxidation and energy expenditure occur in rest. Further on, there are also some points in the method what could lead to a bias. To start with the point that the participants were not allowed to move. They should lay down and the only thing they were allowed to do was breathing. But how realistic is it to let a human lay down for about 2 hours and not even allowed to move a finger? So the participants didn't lay down the entire time without moving something, which leads to more energy used and so leads to a bias in the energy expenditure. The second point is that the participants should ingest the same amount of glucose and sucrose at the same time, so they should swallow at the same time the same amount of milliliters. That's hard to coordinate, so the participants did drink in total the same amount and within approximately the same time, but it is never as accurate as when they should get it injected, for example. The end conclusion of this research is that we can state that glucose gives a higher energy expenditure at rest than sucrose. But the aforementioned points of bias need to be considered. Thus, for a more generalizable answer, there need to be done more research with more participants and a method with more technological devices.
Extermination will be the Krebs cycle and total oxidation. Glycolysis. Come on, sugar for the breakdown. For the breakdown. Glycolysis starts with investment of 2 ATPs to the glucose that we started with. The product is cleaved into 2 G3Ps from which the cell harvests NADH and ATPs. This anaerobic pathway is respiration's first phase, billions of years old, evolved in ancient days before O2 accumulated in the seas, before eukaryotic cells arrived on the scene. It's everywhere, ubiquitous in every organism. Bacteria, sequoia tree, no matter your metabolism, happens in the cytoplasm, doesn't need no organelles. You want to find glycolysis? Look in any cell. Glycolysis. Come on, sugar for the breakdown. For the breakdown. Glycolysis. Come on, sugar for the breakdown. For the breakdown.